Hey, what's up, guys? We're going to look at specific latent heat. So let's look at the definition first of all. Specific latent heat is the energy required to change the state of 1 kilogram of a substance. So where does the name come from? Well, in a previous video, we looked at the heating curve, which is where we heat up solid ice and we melt it into liquid, then we heat the liquid up, and then we boil that liquid into a gas, and we look at how the temperature varies with energy or time. There's a couple of really interesting points on this graph, and it's between points B and C and between D and E. Between points B and C, the substance is melting, and between points D and E, the substance is boiling. And what's really interesting here, and what confused scientists, is that even though the water was being heated by a heat source, the temperature was staying constant. This was confusing because they thought that if you were heating it up, the particles would always gain kinetic energy and therefore the temperature should increase. But what happens at these changes of state is that energy goes into increasing potential energy instead of kinetic energy. Therefore, the temperature remains constant when a substance changes state. And this is where the name latent heat comes from. Latent means hidden. It means that this energy was going in, but the scientists couldn't see where it was, so it looked like the energy was being hidden away inside the substance. What was actually happening was the energy was going in, and it was increasing the spacing of the particles and increasing their potential energy. So that covers the latent part and the heat bit, because it's there how much heat has to go in. The specific bit is the fact that the latent heat of a substance is specific to a particular substance. So if I've got 1 kilogram of water, it has a very specific latent heat. And the latent heat of fusion, which is the energy required to melt 1 kilogram of ice into liquid water, is 334,000 joules per kilogram. So if I have 1 kilogram of ice, to melt that 1 kilogram of ice into liquid water, it will take 334,000 joules of energy. The latent heat of vaporization is the change of state, which is from stage D to E in this graph, the boiling change of state. And the latent heat of vaporization is 2,260,000 joules per kilogram. So if I have 1 kilogram of liquid water and I want to turn it into 1 kilogram of steam, it will take that much energy. And if I have more mass, it will take that ratio of increase of mass more times the latent heat of fusion or vaporization. So a little quick recap. Specific latent heat is the energy required to change the state of 1 kilogram of a substance. We've got a number of different changes of state. We have going from a solid to a liquid, we have melting. Going from a liquid to a gas, we have boiling. And then we have the reverse. Gas to liquid, we call condensing. And liquid to solid, we call freezing. And because of these different changes of state, we have to use two different versions of latent heat. We have the latent heat of fusion, which is what we use when we're looking at melting or freezing. And we have the latent heat of vaporization, which is what we use when we're going from liquid to gas or from gas to liquid. I mentioned that it's specific to a material. So in this table on the bottom, I've got some different materials. Water, for example, takes 334,000 joules per kilogram to melt, whereas mercury only takes 11,000 joules per kilogram to melt it from solid mercury to liquid. We've also got the latent heat of vaporization, which is where we're looking at boiling or condensing. And to boil 1 kilogram of liquid water into 1 kilogram of gaseous steam, it takes 2,260,000 joules per kilogram. And you can see it's different once again for alcohol and mercury. What's important to note is that the latent heat of vaporization is always greater than the latent heat of fusion. And that's because to turn a substance from a solid to a liquid, you're only increasing the particle spacing a tiny bit. But to go from a liquid to a gas or vice versa, there's a much greater change in particle spacing. So the equation which involves specific latent heat is actually very simple. We have energy is equal to mass times specific latent heat. We use E for energy, we use M for mass, and we multiply by L for specific latent heat. But if the question wanted us to work out the mass, we would cover up M in our formula triangle, and we'd have M is equal to E divided by L, because we always start at the top of our formula triangle. And if we needed to work out the latent heat, we would cover up L in our formula triangle, and the latent heat is the energy supplied divided by the mass. What's really important to always remember is the units that we use. So for energy, we use joules. For mass, we always use kilograms and never grams. And specific latent heat is always measured in joules per kilogram. As I've mentioned before, we've got the different states of matter. We have solids, liquids, and gases. And we've got to use latent heat of fusion when we're going from solid to liquid or vice versa. And we use the latent heat of vaporization when we're going from liquid to gas or vice versa. Going from solid to liquid, we're putting energy in. So the energy in is equal to the mass times LF. And if we were going from a liquid to a solid, the energy would be given out because the particles are reducing in their spacing, and that would be MLF. Those two quantities are equal to each other. If we're going from liquid to gas, we're going to use the latent heat of vaporization. So the energy supplied in to go from a liquid to gas is the mass times the latent heat of vaporization. If we've got a gas and we convert it into a liquid, energy is going to be given out from the substance, and that is going to be MLV. So it's really important to use LF when you're going from solids to liquids or vice versa, and LV when going from liquids to gases or gases to liquids. So let's have a look at a few simple calculations, and the questions are really, really easy with this. The first one, how much energy is required to melt 5 kilograms of water? So we're going from solid to liquid. So we're going to put energy in. So the energy in is equal to MLF. We're going to use LF because we're melting solid to liquid. So now we just put our numbers in. So the mass is 5 and the latent heat of fusion of water is 334,000. So when you multiply those two together, you get an answer of 1,670,000 joules. So it's a huge amount of energy to melt this ice into liquid water. Next question, how much energy is required to boil 2.3 kilograms of alcohol? Because we're boiling it, we're going to have to supply energy in. So the energy in is equal to M times LV. We're using LV this time because we're boiling the liquid alcohol into gaseous alcohol. So the mass is 2.3 and LV of alcohol is 860,000. And when you multiply those two numbers together, you get 1,978,000 joules. Once again, it's a large amount of energy. Please don't be afraid of these large numbers. It does take a lot of energy to change the state of a substance. Next question. How much energy is released when 600 grams of water freezes? So when this liquid water is freezing, it loses its energy. So the energy is going to be M times LF because we're going from a liquid to a solid. Our mass, here it's given in grams. We don't use grams, we need to divide by 1,000, so we get 0.6 times LF, and the LF of water is 334,000 joules. And that gives us an energy out of 200,400 joules. Very simple. This next question is slightly different. What mass of alcohol has melted if 275,000 joules of energy are used in this change of state? So we want to know the mass, and we're going from solid to liquid because we're talking about melting. So the equation for mass, M, is the energy divided by LF. And we're going to use LF because we're talking about going from a solid to a liquid. The energy supplied is 275,000. And we need to use the LF of alcohol, which is 110,000 joules per kilogram. And that gives a mass of 2.5 kilograms. Very simple, very straightforward. This is the last one. 750 grams of a substance require 220,500 joules to change it from a liquid to a gas. So we're boiling it. Which substance is it? This is where we're going to have to calculate the specific latent heat. And because it's specific, that will enable us to determine which substance has been boiled. So we need the equation for L. So LV in this case is going to be equal to the energy divided by the mass. If you cover up L in the equation and start at the top of the triangle, you get E divided by M. So the energy supplied is 220,500. and the mass is 0.75 kilograms. We don't use grams, we divide by 1,000. And when you do that, you get an answer of 294,000 joules per kilogram. And that must mean that the substance is mercury. So we've used the fact that this is a specific latent heat of vaporization. It's specific to this substance. Therefore, the substance that was heated must have been mercury. Really easy, really straightforward. So, in summary, the specific latent heat is the energy required to change the state of 1 kilogram of a substance. It's specific to a specific material. The equation, energy is equal to mass times specific latent heat. We measure energy in joules, mass in kilograms, and latent heat in joules per kilogram. The formula triangle given is here, and you just got to remember how to rearrange it by covering up and always starting at the top of your triangle. Remember that when we're going from a solid to a liquid, we're going to put energy in, and when we're going from a liquid to a gas, we're also going to put energy in also. We use LF when we're going from solid to liquid, and we use LV when we're going from liquid to gas. And vice versa happens. Energy is given out when you're going from a gas to a liquid, and energy is given out when going from a liquid to a solid. So that's it. Thanks for listening. See you all soon.